Welcome everybody, Colin Power here. Yeah, just doing a quick sound check and we'll be with you in a few moments. So get yourself settled down and get ready for today's workshop on squares and triangles coming up shortly. Hello. Is that sound back on now? Hopefully the sound's back on now. Sorry about that. Looks like the sound got cut off. Okay, let me start that one last time again. Okay. We'll have a full start, shall we? Hello. Okay, so hopefully the sound is back on. So hopefully I can go back and introduce myself again. Sorry about that. So let me just check and make sure the sound is working. Yeah, it seems to be working. Ah, it's on. Good. I've got a message from our technical team. Right, I said we were going to overcome our technical problems one by one. Last week we did have a few, and this week it started off with a few more. But there you go. We have the sound back on now, so let's start our presentation. So basically today is about squares and triangle numbers. Now you might think you know everything there is to know about squares and triangles. They were sort of the first shape that we ever sort of started to look at. And today we're going to sort of find out whether that's actually true or not. And hopefully I'm going to sort of dazzle you with a few things about triangular numbers that you might not know about. In the next part after that, we'll be looking at something called parts and wholes. Now, that's a kind of lead into a little bit of fractal geometry, if you like. Yeah, so we're going to be taking you through that journey. And then we're going to be looking at the other side, which is the square numbers. And just so that we don't leave it all as kind of pie in the sky, if you pardon the mathematical pun, we're also going to ground it in some atomic theory. So we've got a little game for you to play at the end, and you can come down to our wonderful classroom here. As you can see, this lovely learning environment we've created. If you'd like to join in with any of our classroom activities today. Just as a quick reminder, if you want to come to our classroom, go to intoinfinity.com/live. That's intoinfinity.com/live, where you can actually participate in some of this stuff. So just before we begin, just have a quick sort of perusey about something about me. Here I am. I'm a bit of a musician, as it were, and that's how I kind of got into a lot of this stuff, through understanding music and drawing with a compass and straight edge. And so I've since then been developing my kind of geometry skills as a way into sort of mathematics, because I found it sort of more appealing for my kind of mind in the way it works. So if you're of that kind of ilk, as it were, then hopefully you too might enjoy some geometric perspective on some of this mathematic. The other thing we could say is that we're also not alone. I've got a core team surrounding me, as it were. I've got Dr. Heike Bielik and Baptiste, who are sort of also running workshops online. You can check Baptiste out tomorrow, and Heike Bielik will be out on Saturday, I believe, yeah, with another fantastic workshop there. So together we form something called Into Infinity, yeah, and a little bit about us. Into Infinity, because we sort of explored the universe and life and all of that stuff through a geometric perspective, we decided that it would be a nice way to sort of apply that to some other sort of learning material. So we try and develop fun and innovative ways to learn about things, about life, the universe, and everything. So we're not sort of scared to go into any kind of boundary with that, because we're an educational group primarily, and we'd like to share that with us. One second. Okay. So it looks like we're all good to go. Just a little bit about our online classroom. Today we'll be running with a service called Discord. If you're not aware of that, that's a kind of chat room. And it's a really nice chat room because it allows us to have a kind of permanent basis for this lesson. So the conversation can continue through that. And if you're not a member of Discord, not to worry, you can just come to our site. And when you come there, you'll find that there's a kind of little line here like that. We've just moved the chat room into next to the main screen, so it might be a little bit slimmer, but they'll find a little line like that, and you can just type guest name in, and you can sign in as a guest. But if you do have a Discord account, you can just sign up to you can just press the Discord button, and we'll automatically log you in to our particular chat that we're rolling today. So that's Discord for you. If you haven't got an account, I thoroughly recommend it. It's a great service for communicating in all sorts of levels with small groups and things like that. They're really great guys. So the other thing that we have in our classroom today is GeoGebra. And GeoGebra is a geometric drawing tool online, and we can use that to draw some shapes. So we'll be using that today as well. So you can either come to our classroom and use it, or visit it on geogebra.com. And so we'll be taking you through how some of that works today as well. And finally, I do appreciate some feedback. So if you do enjoy any of this lesson, then do feel free to come down and use the Flipgrid, we've got which is a video recording message, and send me a video. Let me know what do you think about it, and if there's anything that you've learned today. So that'd be interesting for me to get some feedback, as it were. So, and also to see you. I mean, you can see me, and it'd be nice for me to connect with you face to face. Anyway, some of the best videos, I may even offer a coupon reward. I tend to do that sort of thing. So that's our classroom for today. And what we could say is we're going to move on now to a little bit of another idea, which is our main presentation for today, which is square and triangle numbers. Now that sounds a little bit boring, a little bit square, but I can tell you there's a lot more to squares and triangles than first meets the eye. Let us move on now and find out about these shapes. Just give us a quick overview. Now, you might have noticed that we have circles, triangles and squares, and then you could say that these shapes are probably the fundamentals of form in the second dimension. Second dimension means a flat plane, so we call that a shape. So a circular shape, some people say, has 0 sides or an infinite number of sides. Actually, if you think about it, a circle can have an infinite number of sides, really. But it looks like a 0, and all the sides connect in a nice curved space. That's what makes it this perfect form. Quite unique from all the others. On the other hand, you could say the triangle here, well, that's the kind of smallest shape, if you like, with just 3 sides, and then the one after that, number 4, is a nice square shape like that, and so if you think about it, these shapes have various qualities, Now you might have, remember, if you've ever been a child, you were sticking objects maybe into sort of certain shapes and learning about these things from a very early age. So you might be saying, Colin Power, what could you teach me about that sort of thing? Well, let's have a little look, shall we, what we've got lined up for you today. So we're going to be mainly talking about just the square, just about the squares and the triangles today. We're going to leave Mr. Circle. We could do a whole workshop on circles, but we're going to leave Mr. Circle over here for a second as we move on into infinity. Here we are. So what can you say about these two shapes? So it'd be nice for me, to sort of lay that question out at first, so we can sort of start to think about what sort of things we do know about. Now, I'm not going to leave it as just a sort of open-ended question. You can obviously pop in something into the chat, but I've also prepared over here with Mr. Lightbulb here. If you go to the little light, if you go to our classroom into infinity.com/live, you will see that there's a little light bulb here. And what we've got is our friends at Answer Garden, who are very cool, have actually left us the ability to have a little brainstorm. So there's all the things that you could say about triangles, and you can put that over here. Anything you can say about a triangle, you just type your answer in there and you press enter, and then your answer will appear below along with all the other people's answers, and you can see exactly what they're up to. Only see me. Okay, sorry about that. There we are. Sorry about that. Obviously, the thing transitioned a little bit strange, and once again, I've been left in the dark. Don't worry, one day I'll afford an engineer. I won't have to worry about engineering myself. It's always a bad idea if you're a musician to engineer yourself. You know what I'm saying? Anyway, in the meantime, what we could say is I was just sort of going through our presentation. What can you say about these two shapes? And so these two shapes, the square and the triangle, you might have said, I can't really tell you that much about it. However, what we could say is it's got 3 sides. Let's have a little look here. Let's have a look here. There are 3 sides, 4 sides. That's a quality of those shapes. So let's go over to our. I said we had a little answer thing. If you go up here to their little light bulb, and here we have. What can you say about a triangle? So let me type 3 sides. I type 3 sides in there. And I press enter like that. And I come up with this thing, type another answer, So you can see what's happening here is I can keep adding answers, and I can say over here 4 sides, That's one thing I could say about that. And you can see in here, it will start popping up 3 sides, 4 sides, and so and so and so and so. And the more answers that we create, the better. Let me just do a quick reload so it sort of stays in the center. What else could you say about a shape, like a triangle and a square? Come over to our classroom at intoinfinity.com/live and have a go at typing in your answer, and we'll see at the end of the show how many answers we can accumulate in our little brainstorm, and how many answers were repeated over and over again. We can have the same answer more than once, by the way. So what were the most popular things that people knew about squares and triangles? So here we are, back to our presentation for a second. I'm going to move forward just a little second. Here we are. So what can you say about these two shapes? That's the question for today. Now, I would like to start by offering one thing that we could say about these two shapes. Yeah? Here we have a triangle, and the triangle is the same size as the square, and the side length is the same. Yeah? So exactly the same side length there and there. And we've got two parallel lines here. Yeah? So what does that say? So if we place the square, let's place the square firmly in there. There's a square, and then it's placed itself there. And what you can see is the square fits nicely in between there. And I could slide the square. Imagine you could push the square down the tube, couldn't you? You could push it or push it up the tube, and it would slide in either direction. That's a sliding motion, like that. Zoom, 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 zoom. And that gives us something we call about the quality of a square. It's that two parallel sides that have that quality, and that allows it to slip between the two spaces, yeah, in the space here. So what about the triangle? Let's have a look. So this is the triangle, same size, but oh, there's a small gap under here. That's interesting. It means that the triangle must be slightly smaller than the square. Well, that seems fairly obvious, doesn't it? But what might not seem quite so obvious is that you can actually roll the triangle down the same width of space. Yes, the triangular wheel. Bet you didn't think about that, hey? So when somebody first invented the wheel, it was based on the circle. Probably didn't also realize we can base the wheel on a triangle. And if you look into this sort of thing, you can see that actually the central point is actually rotating around the center. Look, see, it's actually rotating around that center there. If I hold it there, it's going above it, it's going below it. So what's really going on there is actually we've got the central spike rolling around itself in a little circle like that. Now, if you could think about vortices, you might find out there's some interesting things there about vortices and triangular wheels. Anyway, that's a little clue for some things today for some people to look into a little bit more. But it might have some sort of relevance in some sort of engineering sense, and we can have a look. You know, if you want to have a little play with some of those things, I'm sure you can. So let's just go to the next one. So you could say the triangle, we always mentioned this, was the smallest shape, yeah, right? Yeah. And actually the circle, we said, was the largest shape, and therefore you can see, put a triangle with a circle, and somewhere in between there's a sort of curved space that sort of rests in between there that gives the triangle this rotational quality. Fantastic. So we've always said that triangles are kind of rotational. If you start at the top there, let's say you went from this point here, how are you going to move to the other point? Well, we've only got two choices, haven't we? Left or right. That's right. So we could go down to there, or we could go down to there. And it's pretty much like that, you know, if you think about those choices that you have in life, you can either choose to do A or B, yeah? Or should we say we only choose one thing? This is the infinite of possibility, and so we choose one thing out of the infinite possibility of choice that is presented to us in each moment, yeah? So you could say, actually, we can go round and around and around the triangle from one point to the other here, and it's actually it's also, you know, quite sort of infinite, you could say. We call that infinity around. It keeps going from one point to the next point, and it's very hard to find the center. And that's why we call the triangle in our sort of system something called a sustaining force, because you can't find that center. It just keeps going around and around, yeah? Now, we also use triangles to triangulate things, yeah? So you can triangulate any point inside of here, yeah? And you can work out where it is, yeah, just like on a sort of grid. As a dot moves around, there it sort of goes and triangulates, yeah. And we use that for satellites to find out where we are on planet Earth and things like this. So lots of things there about triangles. Okay, well, I'll tell you what I do, yeah. Let's have a little look at numbers now, yeah. So triangle numbers, yeah. So look, here we have a nice circle, nice little dot. The dot just sits there and goes around and around there. But actually, it's a thing of itself as well. It's a number, isn't it? We could put the number 1 here, and we could put the number 1 here. So let's imagine actually we moved on from the circle, and we went on and said, well, let's place 2 circles beneath it. What do we get? Well, actually, we get a nice triangle, don't we? We get a very nice triangle there. We've added to the 1 circle, we've added 2 circles, and that's given us a total of 3 circles, which makes a total of a triangle. So we've got this nice little triangle there. So you could see, oh, that's quite an interesting pattern that's emerging. I wonder what's actually going on. So let's move on to the next one. So we add another 3 circles, 1, 2, 3, and we get a triangle of 6 in total now, yeah? So you can see what's starting to happen as we move through the numbers, 1, 2, 3, we're getting a total of 1, 3, and 6. What will the next number be? 4? That's right, it's going to be 4, isn't it? Yes. So the number next there will be 4, and that means the triangular number will go up by 4 and will become 10. So you can see, look, 3 plus 2, 1 plus 2 is 3, yeah? And then we move again, mouse is acting up, then we go again from 3 plus 3 is 6, and 6 plus 4 is 10. So there's a pattern to these triangular numbers, and that sequence there can carry on into infinity. It's a particular way of looking at things. On the other side here, each row itself has a whole number, 1, 2, 3, 4. It's a very simple pattern, isn't it? Yeah. So you can see that triangle numbers include all of this numerical sequences in them. So let's have a little look. What's actually happening here is the triangle is moving in a certain direction. Now, let's find out something new about a triangle as well. It doesn't just have to move in one direction. There's no reason why it couldn't have started here, 1, then added on another 2 there, added on another 3, and added on another 4 to take it in another direction through there. And the same would be if I went through here. So you can see here, actually, the triangle has more than just a downward direction. It actually has these 3 directions in which the movement of adding additional shapes can push it through space, if you imagine that, yeah? So there we are, sat in, there's a central one there. And it's sort of saying, which way shall I go? Well, it could go in any of 3 directions, really, you know? You can think about it, it's in the middle, isn't it, yeah? So triangle numbers are very interesting, yeah? And the more you start to think about this sort of stuff, the more you can sort of realize there's more to triangles than meets the eye. So hopefully I've had a chance there to sort of open your eyes to a few things about triangle numbers, yeah? So on the triangular number line, triangle line, what we see then is that triangle numbers are actually made of a sequence of number right the way through to infinity. Yeah, it's just it's a normal number line, and we use it every day. We use 1, 2, 3, and we use that to generate everything in mathematics, don't we? All of those numbers, those whole numbers, are what we're using to we call them sort of natural numbers, if you like, yeah, or they could be, some people call them whole numbers, but not quite, because it doesn't include the number 0, yeah? So actually, these are the natural numbers that are being created, yeah, in this direction. That's how we have defined them in mathematics, yeah. I'm learning mathematics slowly. It's very difficult for me. Anyway, now the triangle wasn't just, it's not just me who's sort of, saying, well, actually there might be something quite interesting about triangles. In fact, if we go back to the ancient Greeks, we find that tetracities, yeah, I think I got that right. It might not have done. Please correct me if you know how to say it properly. I'd love to know. I don't speak Greek, but there we are. So anyway, we could say actually these guys, the Greeks, had this name for this triangle, yeah, this set of 10 dots, yeah, and it was so important to them. They actually even had an oath that they swore when entering into one of the Pythagorean schools that was set up. So I swear by the discoverer of tetracities, which is Pythagoras, yeah, which is the spring of all our wisdom, the perennial font and root of nature. So that gives you an idea about the level at which these highly advanced mathematical universities were considering some of these ideas behind shape. Now, triangle being the smallest shape, as I said, obviously held a lot of interest for the Greeks, yeah? And so they actually developed quite a lot of mathematic around that stuff. And if we remember that mathematic also goes on to become the basis of our scientific foundations that we use today to qualify, the mathematics and the science that we're using. Yeah. So the origin, you could say. Yeah. So from the tetracities, you could say that we can place actually numbers 1, 2, 3, 4, 6, 9. Yeah. 8, 12, 18, 27. Yeah. And this gave a particular formation to the thing, where you can see down the side here 1, 3, 9, 27. You can see that's a 3 times table, and 1, 2, 4, 8. That's a 2 times table. Now the Pythagoreans were very, very much into dividing things or doubling things and tripling things, or dividing into 3. They were very much into that because that's the basis of the Pythagorean music system. And we're not going to go into that in a great detail right now, but what we could say is that there's some very interesting numerical stuff that's going on here. Yeah? In future lessons, we will go into quite a lot of detail about how music works through this system, so plenty to come on that one. But one of the things I'd like to bring our attention to is that there's more stuff than in these numbers than meets the eye. For example, if you sum up the total, it becomes 84. Well, that's an interesting number, isn't it? Yeah, number 84. And if you look at here, we've got 10 dots. Yeah, so 10 dots making a number 84, right? Well, that's quite an interesting one. And if you just take these ones here, which are of particular interest, yeah, with number 6 particularly, yeah, we get a total of 36. So lots of numerical stuff, but what does that actually mean? Well, if we have a think about it, they didn't really know too much about the periodic table. Well, now we know quite a lot about the periodic table. We've managed to qualify every single atom on the periodic table, and we know a lot about how they work. And it just so happens that when we get to element number 10, yeah, which is this, if you imagine the 10 dots, we get neon, which is a noble gas. And now noble gases are very special in the sense that they don't react. So they kind of create these boundaries between, say, one shell and the next, where you can't get lower than that shell. And so everything in chemistry builds on the shell before, And once that sort of shell is full, it's very difficult to remove anything from it. They become noble. Noble gases do not want to react with any other atoms, so they just float around on their own. Yeah, and that's the way they work. So that's why they have notable importance. But here we have another noble gas, krypton, yeah, which is another noble gas, and you can see that those central numbers there equal 36, which also is krypton, that noble gas. Once again, it's one of those noble gases that forms one of the boundaries within the atom. And lastly, you could say the whole sum is 84. Well, interestingly enough, that just happens to be where the first unstable element appears. If you imagine, well, they call it the naturally radioactive elements, yeah? So, polonium, yeah, polonium is 84, and what that does, it's the first one after bismuth that actually has a decay function. Now, to be more precise, actually, we found bismuth does decay very, very slightly, but it took a long while to find because its decay rate is very, very slow. Yeah, which means, what do we mean by decay? We mean the atom is actually falling out of existence. It's giving away its energy, and it can't hold on to it. And so by the time we get to lead, number 82, we get to a relatively stable atom, and it won't give away any more of its energy so much. It will just stay there, and it will just be the atom it is. Yeah, and it's worth bearing in mind that all of this periodic table actually goes to form the whole universe. So if you think about this, what they were saying about this stuff, yeah, when they did all this mathematics, Plato came up with a name for it. He called it the lambda. Yeah, lambda. Yeah, and basically, what he said about it in his Timotous is God created the cosmic soul using two mathematical strips of 1, 2, 4, 8, and 1, 3, 9, 27, and we can see that runs down the side there, and that leaves a space in the middle for the whole of creation to manifest itself. And actually, we can say, in a sense, not to say it's 100% true, but we could say there is a kind of metaphor there that we could unify with some of the stuff that we're talking about in the periodic table. The periodic table is the basis of matter and life. Yep. So there we are. That's a little bit about Plato's lambda. Yep. So also, as well as defining, I'll just take that back, as well as defining, you could say, the atomic structures and the actual periodic table, they noticed, and this is what the Pythagoreans noted, that it also defines dimensions of space. Yeah? So this model here, for example, we start at 1, and you could say that's a 1. This is point, it's a single point, it's that dot that starts the triangle, yeah? And as we move through, the next one will be 2, 3, yeah? And we call that linear dimension, yeah? Like a line, yeah? So it goes vroom, 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 yeah? So, yeah, because you've got to the power of 1 to the power of 1. And if we moved up again, you can see that the next point, yeah? Because you follow it through logic, yeah? 2 squared is 4, and 9 is 3 squared. Yeah, so that gives us another example, doesn't it, of how these now we're moving into a square dimension. We call that squaring, don't we? Yeah? So they said that's a surface. Yeah, when you times something by something or something, it turns into a surface. Yeah, and finally the last one was cubic volume. Yeah, so yes, when we take something to the power of 3 or the power of 3, we call it cubing. Yeah, and those are geometries. They are geometries of a particular type. So you can see why they thought that these, because obviously the cube was a Platonic solid and it held a special relevance. They didn't have quite 4D shapes and all of that stuff. So, for them, that was the edge of the universe that they were reaching, yeah, in this kind of mathematic, yeah. We've formed 3D, and that's what we're in, yeah. And so, in a sense, what you could say is, from the level of understanding, this was held very, very much a lot of significance, this triangle. So there's a little something about triangles themselves. Let's have a little go now at maybe doing some drawing, shall we? Yeah. Let's just go through. Yep. So we'll go over to here, yeah, and this is GeoGebra. Yeah, this is GeoGebra, yeah. And GeoGebra is an online geometry drawing program, and you can have a go at drawing some of that stuff with us today. One sec, let me just check we're on. Yeah, we're good. So, here we are, there's a circle here, and there's other tools here that we can use to draw geometries, yeah. And the one that we're going to look at today is just the circle. Yeah, and what we're going to find out is how easy is it to draw a triangle with a circle. Now, you don't have to follow along with the computer software. If you've got a compass at home and a piece of paper, you can run and go and get it now, as we just explained to the other guys who are going to be using this, how it works. Yeah. So, if we think about the circle itself, yeah, what we want to do is get our compass and we click on this thing here. And we place there a dot. You see, it says A, yeah, because that was the first thing that happened, yeah. And then we can see what I mean. As we draw this out, as we draw this in and out here, we can see that the circle gets bigger and smaller. And that depends on how far away my mouse is from the origin, yeah, which is A. Yeah, if I'm over the origin, I get just a dot. And if I move out to the edge, I get a proper circle. Yeah, so let's choose a point there. That's point B. So we have a distance now between A and B, and we call that the distance of 1. Yeah. Mathematicians generally define pi as being the distance across here, but in metaphysics we define it as being 1 here. Actually, not just me who's saying this, lots of other people are agreeing with me that actually pi should really be considered as the radius, yeah, because that's where we work in geometry. So if you work in geometry, the radius of the, seems a better calculation. So by clicking on the B one again, I can create another circle, right? And so, in other words, if you had a compass, without changing it, you could just swap over and put the point on the edge of the circle, and we can then draw another circle, and that circle will pass through the center, yeah? So then we have this lovely little shape there, yeah? And we can talk more about that shape. It's called the vesica Pisces. We can talk more about that shape in future lessons, yeah? But we're going to carry on for our third circle. Now, where the two circles cross, you could say there is a point here and a point there, yeah? So what we could say is we could use one of those points. Let's choose the one down here, and we're going to have to, oh, didn't quite get that on, did I? Let's just undo that, yeah? Sorry about that. Let's get in there, and we want that intersection. Make sure we're on the intersection there, yeah? And then I can click on there, right? And we create something there. Now, can anybody see the triangle? You can. Oh, fantastic. Well, I'm glad you could see the triangle, yeah, because that means you have a geometric eye. Now, fantastic stuff. Now, look, I'm going to go over here and click the Move button, and you can see I can shrink the triangle by moving one point. Every point remains relative, and particularly in geometry of this nature. And so it didn't matter how big I opened the original circle, it would be a big triangle or a small triangle, yeah, but it's still going to be a triangle, yeah. Let's see if we can draw in the triangle. Now, in order to do that, I've got this nice little thing called a polygon, right, yeah. And so what I'm going to do is click on the polygon, yeah, and I'm going to click on one node there. I'm going to click on one node down there, if I can get it. Ooh, my mouse is a bit funny. There we are. There we are. Let's see if we can get the mouse. I do need a new mouse at some point. Here we are. And there we are. We have a nice triangle, yeah? Okay, yeah? We can also color that triangle. Let's make him nice and blue, yeah? Maybe we'll go here and just maybe have a look. We'll have a look at the color in a second. So there's a nice blue triangle there, yeah? So there we have it, yeah? So we can see that what we've done there is actually turn a circle into a triangle. And that's quite an interesting thought, isn't it, yeah? And once again, as I said, it doesn't matter if we move the points, yeah? If we move the points, it's just going to change the size of the triangle. Let's make him a little bit bigger, right? So triangles come out of circles, yeah? And you could say far more easily than squares, yeah? I mean, if you were to think about, if you wanted to turn a circle into a triangle, it's fairly easy. Now, the Greeks probably knew about this because they actually drew with geometry. Geo meaning earth and metry meaning measure. So you can imagine they used to hit a stake into the ground and go around it with a sort of equal measure, yeah, and you could draw something in the sand, yeah. And that's traditionally how you could say when we developed the compass, it came out of that concept, geometry, geo. And so geo means earth, and so they probably knew about how to draw this thing. And so it's no wonder that they kind of saw this triangle as being in some way kind of divine, yeah. So let us move on now, yeah, and just have a little look. You can have a little practice with some of that stuff, yeah. And we're going to move on now to have another consideration about something, yeah. So this is an idea I had, yeah, which is, can we have a negative triangle? Is that possible? That's an interesting thought, isn't it, yeah? We've got positive numbers and negative numbers, but can we have a positive and negative triangle? Well, that's a thought, isn't it? Yeah. Now, if we go into that, actually, we find that we can place let's say the negative triangle could be upside down, the positive triangle could be the right way up. And what happens then is that we have, remember our directions that we had before, 1, 2, 3, yeah, and then we have an opposite going that way from the negative, 1, 2, 3. So, I mean, if you think about a number line is divided, it's a line, it's divided, and 0 sits at the center between one half, which is the negative, and the other half, which is the positive. It sits right slap bang in the center, right? Now, in order to get there, you could see if I place the 0 in the center there, you can see the same thing. When I'm here, and I go there, I'm switching direction. I'm going out that way, and now I'm going out that way. Obviously, it's not a line because it's a geometry, but you can see that the arrows invert. And therefore, it's quite good evidence that we can actually have this concept of a negative triangle, yeah? And what happens when we do that? Well, what happens when we do that is that we had all the numbers here, remember 1, 2, 3, 4, 5, 6, 7, 8, 9, lining up in the positive, yeah? And now we can have all of that lining up in the negative, yeah? And that means our 0 now becomes the center of two triangles, right bang in the center there. So there's a lot of things you can think about that, yeah? So this is the center of the triangle where my dot is, yeah? And we have a negative and a positive, now numerical space moving in two directions. So all of those numbers can carry on into infinity, just as the triangles can get infinitely larger and larger and larger, yeah? So that's triangular numbers. It's all very interesting stuff. So can we have a negative triangle? Yes, we can. Where would we place that? We could actually place the negative triangle, and this is a quite amazing thing if you think about it. We could place a negative triangle inside of a positive one. Oh, right. That sounds quite an interesting thought, doesn't it? A negative triangle inside of a positive one. And if you look at that image, yeah, and we'll get more into this image when we delve into fractal geometry in more detail, you're going to see that this image is actually found in a lot of fractal geometry. Yeah. And you can understand why, yeah, because we're moving in the same similar sort of shape, still a triangle. We've inverted it, but it's self-similar and it's at another scale. So the question of, is this a fractal? Well, yes, it's the nature of a fractal. Yeah, that's what a fractal is. This is, in fact, the most simple fractal you could possibly ever create. And what's more, if we go back to our drawing, we've actually created it here already. Yeah. All I do is I click the polygon and I join up the inner dots now. Yeah, the actual dots there, and there. Can you see? And we make another one. We go, okay, let's turn that one red then, shall we? There we are. Oh, that's not a point. We want to turn that one, red. Yeah. And if you take that there, I can actually turn him a little bit redder. Yeah. If I click that one there, click the paintbrush thing, I can make him a little bit bluer. Yeah. Right. There we are, red and a blue. Yeah. Doesn't have to be those colors. There you go. Yeah. So there we can see what we have is a negative triangle and a positive triangle. Now, I sometimes like to tidy things up a little bit, and you've got this nice little, if you click down on the edit thing, show hide label, yeah, and I can just click on that, I can click on that, and I can start removing some of the labels there, just to tidy the thing up a little bit. Oh, click on that one. Let's click on that one. Let's click on that one. There we are. So you see that looks a little bit tidier now, doesn't it, as well? So, there we have it, a negative triangle and a positive triangle, yeah? Let's just go back to the presentation slightly, yeah? So see if you can, I'll tell you what, let's do a little challenge here. Let's see if you can just draw this very, very simple fractal, yeah? And if you manage to draw it, I would really, really appreciate it if you could go to our classroom and go to the brain. Yeah, you see the brain here, the little lightning. Yeah, and you can sign up for free. You don't need to have an account. You just type your name in. Yeah, you don't need to know who you are. You can do it completely anonymously if you like, and have a go at just uploading on here an image. You can click on here and upload an image. Yeah, have a go. Yeah, and see if you can just upload an image of your drawing. Yeah, we've given you the tools to do it right here, GeoGebra, or you can go to GeoGebra Online. And what you do is you just click here and you can just download as, yeah, and you can click PNG image, for example. That might be quite a good option. And then it will come down, you can name it, and then you can just upload it from your computer into our board here, yeah. And we can always have a little vote on some of the best ones. We can have a little go at colouring it in if you like. Yeah, we like that. If you're in the real world rather than the virtual, we still would love to see those pictures coming out there and see if you can colour them with interesting sort of imagery inside. See what you can do. Yeah, have a little play. Yeah, as it were. It's all good stuff for the mind as well, isn't it? So, bearing all that in mind, we've just said there we can have a negative triangle, and there it is sat there nicely in its opposite position. So we've got, still got that there, it's all going. Yep. So, yep. So this is a positive triangle over here. Let's see how they fit together. So once I had a positive triangle over here, number one, I created another two positive triangles, and we got number two, on the positive side. Mr. Negative comes along and says, hey, you know what? I see a space there. And he appears, so he can appear inside the other triangle, just like a kind of a glove. Let's say a glove is there, and the hand is there waiting. But only when the space appears can the hand move into the glove. That's the only time it can actually do that. It starts to fill the negative space, doesn't it? Yeah. So just as you have a glass, yeah, and the water now can be poured into the glass, and there's a container for the water. Yeah. So that's all like a bit of spiritual thought as well, if you like that sort of thing. Yeah. So once we get to number three, obviously, I'll add another two spaces there. Yeah. So we can go there and we can fill them in. Yeah. Another three over there. Yeah. So you can see that a pattern is starting to emerge. How this stuff fits together. Yeah. It fits together so perfectly. Yeah. And all of a sudden here with our fourth line, we can find that we can have another three over there. So we're starting to see an interesting pattern that the negative numbers are sort of lagging behind by a little bit, if you like, yeah, but at the same time are then reciprocated in the positive, yeah, that's what we call it, yeah, so like the glove reciprocates the hand, yeah, and that's a complicated word, reciprocates, but sometimes it's nice to learn a new word. So everyone, reciprocates, very nice. We like the word reciprocal. So let's have a little think about this pattern then, because obviously there's something else going on, and if we combine the negative and the positive here, something else is emerging. Something else is emerging. Let's have a look. So you can see this top one here was at that first stage, wasn't it? Yeah. So what did we do? We took one triangle, and really we added three triangles to it, didn't we? Added three triangles to it, yeah. And then we had that shape, and then we moved on to the next shape, and really we added five triangles. We added three positive, and we added three negative, and so you can see there we added a total of five, yeah. And what happened after that? Well, 4 positive and 3 negative, and that's a total of 7. So 3, 5, 7. I think there's some pattern here. Do you know what it is? You do. What do you think the next number will be? 9, that's right, it'll be number 9. Yes, exactly, yeah. So there we had our triangle numbers, yeah, and there we can have an idea that these ones are building through an odd series, aren't they? They're an odd series, and this is an even series, yeah? 1, 2, 3, 4, and 1, 3, 5, 7. We've managed to get rid of all of the sort of, should we say, even numbers, and we're now just left with odd numbers, yeah? It's quite interesting to realize that all prime numbers, apart from the number 2, obviously, are actually also going to be negative, also going to be these sort of odd numbers, yeah? These odd numbers, right? So doing the odd number thing, yeah, allows us to take out numbers. So what is really happening here then is that we're adding stuff on this side, adding 1, adding 2, adding 3, adding 4, adding 5. But another way that you could see this side over here, yeah, is another kind of mathematical function, and we call that division. You see, as we're dividing things, we start to generate a different type of number system. See, this is still one triangle, but it's just divided, its side divided into 4. Yeah, so this instead is a triangle which is definitely growing in a direction like that. It's growing out that way, it's growing out that way, it's growing out that way. So all of a sudden, this doesn't have to be growing outwards, does it? It doesn't have to go outwards. We can go inwards towards an infinity in instead by dividing the side. I can divide this side into smaller and smaller parts. I could divide it into 5 parts, 6 parts, 7 parts, and all the same would happen there, and it would just fill with smaller and smaller triangles. And so that's what we call a fractal, isn't it? Yeah, where you can have a very simple pattern, and it could be a simple mathematical algorithm, which this one is particularly simple because it's just using a very predictable number pattern, 1, 3, 5, 7. So it's a very predictable pattern, and so we could we could develop a very simple fractal geometry based on that. So the other question there is when we're looking, why often we don't see the negative space. Yeah, here we have Alice going down the rabbit hole. Yeah, at the same time, her little friend there says, "Do you see the hole?" She says, "I don't." What hole? I don't see anything. And that's a kind of idea, isn't it? Quite often we're sort of counting things in reality, aren't we? 1, 2, 3, 4, 5, and we're not really recognizing the reciprocal space that is fitting inside of that, So that space there is very important, as we've just seen, it actually changes the nature of the numbers, yeah? And it defines whether we're dividing, providing one mathematic, or whether we're adding, which is a second mathematic, yeah? So what we'll do is, let's have a quick recap on some of the things that we've just learned there. So we've just learned about triangular numbers, yeah? And what I said there at the start was that triangular numbers build up into whole numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. When added, we should add that. And when we divide the triangle, we get another kind of triangular number, but it's just using the odd numbers now, 1, 3, 5, 7, 9, so on. Yeah. So there we are. So let's have that's an idea also about the idea of parts and wholes. We've sort of touched on that. And so basically wholes that we're building up, 1, 2, 3, 4, 5, that is a type of geometry. You could say it's building into space. It's growing in space. It's growing in number. But what is the other one? The other one there is the parts, which is you take something, let's say a universe, and you just divide it into infinitely small things until you arrive at something called an atom. Yeah, and that way you've divided a whole universe into one tiny atom. And once we have those atoms, we can build them again and make life, isn't it? So actually, there's a metaphorical perspective here that we're moving through as we move from parts to wholes and understanding the difference between addition and division. Yeah, which are very, very, very basic mathematical functions. So if any of that's if you're interested in any more of that sort of stuff, you can look at some of that stuff online. There's some great stuff going out there all about triangular numbers. Yeah. Let's just go back now to our presentation. And so now we're going to move on to another idea, which is this plane. Now we talked about that. We talked about you square something. Yeah, whether you do like 3 squared, it's a square and squaring. And so you sort of think about the 2D plane as being like kind of flat, like a flat expanse of land, like that, completely into infinity. Yeah. And so the question is then, if we took that plane and we, like, say, divided it, let's say that infinite surface, yeah, and we divided it in a certain way, yeah, and we wanted to color each space just using 2 colors. No more, yeah, otherwise it wouldn't work, yeah. So the question is, how many types of shape that are completely regular, we mean the same sides for each one, yeah, can fill a 2D space, yeah, with just 2 colors, yeah. So now a little think about that, and we'll take a quick 2-minute break while we just get a bit of a refresher, and then we'll see you in a few moments' time, yeah. 1 second. Okay. Welcome everybody back in the room here. So the rain has started to come down here in India, so we're all in a little bit of the wet. So I hope things are nice and dry where you are, and I hope you're enjoying this workshop. Now, just to give us a quick recap, my name's Colin Power, and basically today we'll be looking at squares and triangles, as they say. Squares and triangles are some of the most simple shapes that we could possibly imagine, if you think. The first ones we ever learned about may be the circle, yeah, but there's a lot we could say about the circles, and we can do a whole presentation on that. But first, something a little bit more tangible, squares and triangles. So if you've been with us or you've missed various things that we're doing so far, let's take you over to the classroom. I'll try and take you over to the classroom anyway. Here we go. No, still not there. Okay. No. Yes, there we are. We're in the classroom. Right, sorry about that. It does appear that I've put myself back up. So there we are, back in the classroom. You can see we've had a few people on the chat. Yeah, I'm actually joining us on the chat room with Heike B and everybody else, and Baptiste. So hi guys, thank you for joining my lesson here today. And we asked a question: out of all the regular shapes, how many can fill a 2D plane by themselves using only two colours? And it's actually, you might seem like quite an obvious shape. On the one hand, there's actually just two. Yeah. Sorry, a little message from Matt there. Hi Matt, for tuning in. Sorry about that, bro. We on India time. I'm getting very confused about times at the moment. So hopefully, hopefully I'll get a better time for you guys back in the UK. Don't worry, I'm going to run some of this stuff again. This is all my kind of first time around, if you like. Yeah. So yes, I'll just recap on some of the things that we've looked at today. Yeah. So we had triangular numbers, yeah, we talked about that. And what we said was that triangular numbers are actually a way of counting, yeah, they're a way of actually producing whole numbers, yeah. So we said triangle numbers 1, yeah, goes down to 2, 3, and 4 as we add rows on, yeah. So we get a whole number series coming through here, and we get a different number series, and these are called triangle numbers here at the side. But you can see their basis, if you can see over here, just comes from the simple 1, 2, 3, 4 on into infinity, and it goes down that way, but it could just as well go up that way. And what I said about that was that, you know, that's going to create an infinite number of whole numbers going this way, and we call those natural numbers. Then the second thing I mentioned is that sometime in the past, that the ancient Greeks enjoyed their sort of geometry quite a lot and used a lot of it for their philosophy. And Pythagoras discovered this, and it was actually in their oath. Yeah, the discovery of the tetracles was how Pythagoras was known. Yeah, which is the spring of all our wisdom and the perennial font and root of knowledge. Yeah, and there's a lot to be said about that. Yeah, because there are certain numbers here, and they can be related to the periodic table. So I said that there's 10 dots, yeah, that's neon, it's a noble gas, and you can find out about that online. 36 is krypton, it's another noble gas, and 84 is the first unstable element on the periodic table. After that, we get all the naturally radioactive elements occurring. So thanks, Matt. Yeah, great to see you on board. And so here we are, and we could say that the Labna was Plato's Labna. He created that, and he said God created the cosmic soul using two mathematical scripts, and here they are rolling down there and there. And in future presentations, I'll explain how all of that links to what we call music and the modern music that we use today, and how this Pythagorean system of music comes out of this triangle. Yeah. So you can see why they were sort of fascinated, because they're fascinated with music, and music was a divine thing back in those days. They saw that as sort of like a sort of numerical mathematical tool they could use. Yeah. You only see me. That's a strange thing. Sorry, I just got a message there saying you only see me. I just have to check our system a second, very quickly. Okay, let me just try that again. Let's try and bring that back. Hopefully that's sorted that problem, hopefully. So Plato's lambda, yeah. So lambda. So there it is, yeah, and it had these divine numbers and divine ratios, yeah. And also, what it does is it defines the nature of space. So we had 1, a single point; 2, 3, the linear dimension, because it's just to the power of 1 to the power of 2. To the power of 2 coming in underneath 3 here, which is like the 2D surface, and to the power of 3 here, which they saw as the cube, which they thought was the end of space in a way. Yeah, a cube was what they call a platonic solid. We can find out more about those as you continue learning through us. And then I asked the question, can we have a negative triangle? And I said, well, we could place one over there and that, and we get a nice kind of negative. You say this was flowing in one direction, and this is flowing the negative triangle in another direction. So you can say that actually, yeah, the triangular, as we saw before, you can build them from various angles, yeah, and the red one here is going in exactly the opposite direction to the blue, yeah. So that's the blue one. It's building from one corner down there in the bottom to that side, or it's building from a corner there, or it's building towards there. And if we go to the other one, then it's building from there and there. And you can see by switching the two, if you look at the center, keep your eyes fixed in the center there, yeah. As it switch, it's going from there to there to there, and those are different orientations in space, aren't they? Yeah. They're different orientations in space. And so what that means is we can actually create not just the whole set of positive numbers, but also the whole set of negative. No. So there, can we have a negative triangle? Yes, we can. And previously I said we came over to GeoGebra and we saw how we can draw the negative triangle very simply from a set of 3 circles inside a positive triangle. So that's GeoGebra there. If you haven't had a go with that yet and you want to get into some of this stuff and you haven't got your compass and set square to hand, you can come to our classroom intoinfinity.com/live, where you can enjoy some of the technology here, where you can create some of these imagery. And I did suggest that if you go here, you can export the image here, and you can upload it to our little light bulb, or the brainy thing. There we are. And here we are. Look, we've had some pictures come in already. Look at that. Fantastic. I did actually say, here, can you draw it with just compass and straight edge? Here we have our triangle. And look, someone here has managed to draw a square. Fantastic. So already coming in there, that's fantastic stuff there. Look at that square, but it's very different. You see how many circles we need to create that square. We're going to get onto those in just a second. Yeah. So if we look at the one before that, this is our triangle. Oh, it's the other way up. Yeah. Yes, it could be the other way up as well. In that case, the positive triangle in the middle, the negative triangle on the outside. Okay, sorry, I might have had a little glitch there in the old internet. So I hope you're still with me. Yeah. So those are our submissions for the moment. If you've got a submission yourself, to have a go and see if you can draw an infinite triangle. Now, why I say infinite is because yes, this is the beginning of fractal geometry. Yeah. And as we go through, we can see that positive triangles allow negative triangles to exist. There's a kind of, like I said, a hand that fits the glove. Yeah. And so these spaces here, they're actually spaces. And when we start to look at those spaces, we saw a certain number pattern, 3, 5, 7. And we said the next number, well, it looks like it's going to be a 9, and it is. It's 9. Yeah. So actually what's happening here is that we're building just 1, 2, 3, 4 normal numbers, and 1, 3, 5, 7. Well, that's all the negative. That's all the odd numbers, isn't it? Yeah. So you can see that there's a correlation here. We see that through the process of addition, and we see that this one here is a process of division. Yeah. So there's 2 processes going on. Yeah. So question: do you see that hole? Yeah. And Alice is saying, "What hole? I don't see anything." And there we are, and we can say that's a kind of state of the world in a way that we often don't see the spaces that are created inside through the process of division. And we'll get into why that is in a short while. Yeah. So I said there are 2, let's go back to where we are now. We said there are 2 types of regular 2D. Did you get which ones they were? Let's have a look. Well, one is actually the triangle. Yes, of course, because we just saw how the triangle can actually get smaller and smaller triangles, and it all fits perfectly together with just 2 colors. Yeah. And the same goes for the square. The square is the other one. Now you probably know that because you know about the chessboard, but there aren't any others. That's it. That's the limit. So really, actually, when we talk about this sort of stuff, this triangle here and this square here are the only way that we can fill a 2D space with 2 colors. And that's very important if you think about what is it that limits the universe. Yeah, the universe is infinite, and yet at the same time it seems very limited in some respects. You know, things are things, and there's only a certain number of those things. So yeah, we have a finite number of resources on planet Earth, and yet at the same time we're bound within an infinite of space. Yeah, and here we see the concept embodied within a triangle and a square. Yeah, so I tell you what, we'll do have a little bit more look into our square now. Why not? Yeah, so we started off with a square over here. We could add 3 more squares to it. Yeah, and we get a larger square. Yeah, we start, and then to that we can add another 5 squares going around the edge of the square there, and we get a larger square, and then finally we could add another 7 squares there, and we get another one. What's the next number? Yes, that's right, it's 9. Yes, 9, that's right. So 9, hold on a sec. That's a pattern, isn't it? I remember now. I had a pattern there. 3, 5, 7, 9. I'm sure I saw, we did, didn't we? We saw that with the triangles. That's bizarre, isn't it? Yeah. So what have we got here? We got odd numbers. And the question is now, can we have the negative numbers? Now, I would sort of point out at this stage that negative squaring is not a particularly well-recognized mathematical fact. Yeah. So the question is, can there be a negative square, is quite an interesting one from a mathematical view. Yeah. Let's have a look. Generally speaking, in mathematics, you could say you can't have a negative square, because when you times the number 2, or negative 2 by negative 2, you get a positive. Yeah. And when you times 2 by 2, you also get a positive, because 2 negatives make, unless it's positives, you have 2 negatives, it makes a positive. And therefore, you could say, no, you cannot create a negative square. And it was on that basis that a lot of mathematics has been formulated. So, for example, if I said, what's the square root of -1? Does anybody know what number that's called? Well, you might not know it, but actually it's called the number I. The number I was a very, very important number because it allowed us to have something called the complex plane. And once mathematicians had found the square root of -1, they thought was the whole complete number system. Now, I don't necessarily actually agree with that. I think there's quite a few numbers that are missing. But anyway, the idea of a negative square then has been sort of relegated to an impossibility, yeah? Because obviously no 2 negative numbers make a positive, so where would that appear? It would appear on number 2 on the positive side. So you could say on the positive side, number 2, that's where it appears. So obviously, let's move that one over to the positive side then. And how would we create a negative square? That's a good question, isn't it? How would you create a negative square, right? Well, let's have a think for a moment. If I took one side and made it negative, and the other side and made it positive, we would get the square of -2. Well, that's a great way to sort of make a negative square, isn't it? Yeah. We just need to have enough on the negative side, let's say 2 on the negative side and 2 on the positive side, and if we multiply those things together, then the square will pop out on the negative. Yeah. Now, it looks a little bit imbalanced, this image, you could see, so we might be able to bring one more in. Let's bring that one in here. Yes. Here we are. This positive first, and now this negative second. It also equals the square root of 2. Now, in my view, that forms a much nicer image. Yeah, and for those people who are into a little bit of mathematics, could see actually there's a possibility there of a -2 square, but it depends really on how you define square numbers, and that's an interesting thought, isn't it? We define mathematics through axioms. Yeah, axioms are the basis of mathematics. Yes, the basis that makes mathematics work. And so if we define our axioms in a certain way, then we can only have positive squares. But if we look at the number line in a slightly variant way than we would normally, we find we can also have negative squares, right? Now, outside of the realm of mathematics, you could say we had a square and a triangular number, yeah? So let's see what happens there, yeah? Well, we have a negative and there in the middle, yeah? And we have positives on the outside, and we've got 4 triangles, as you can see, yeah? And as we see there, we've got now 2 negatives and 2 positives, yeah? Well, that's also 4. But the ratio is different, isn't it? And this is a key difference between the 2 different types of shape. That a triangle will only have 1 negative, and a square has a nice balanced 2 negatives. Just have a think about what we would do if we said that was a negative square, and that was a negative square, that was a positive square, and that was a positive square. One of those could come out of positive, positive. One of those could come out negative, negative. One of those could come out negative, positive. And one of those could be positive, negative. Was that too many positives and negatives for you? Well, let's just go back then and have a quick look at the other page here. You can see what I mean. We could actually put this equations would nicely fill that square there, wouldn't it? Yeah. So there's a nice kind of little image, isn't it? Yeah, to have a think about that this here can actually be quite a good representation of negative squaring. Yeah. But obviously when we go through to the next level, we've got a little bit of a different scenario because there's now 4 of these negatives to 5. It's a bit of a different, it's suddenly become imbalanced, yeah? Whereas actually 1, 2, 3, 4, 5, 6 positives to 3 there, yeah? So you can see the relationship is different, but overall the sum total still to 9, okay? So as we move forward on there, we could say we get 16 and we get 16 on the other side. Now, this is all very, very, very interesting when you kind of think about the idea of squaring. Now, does anyone know what a square number series is? Yeah. Well, generally we take a number and we square it and we say that's the square of the number, yeah? So if we squared number 1, that would be 1, yeah? Well, if we squared 1, it would be 1. If we squared number 2, we get 4, and that's that number there, and it's that number there. And if we squared number 3, you could see we get 9, and so on. 4, 6 times 4 is 16, 16. That's the square number series now. So let's go through. We've actually been able to start from a triangle with a single number, 1, 2, 3, 4, 5, 6, 7, going on to infinity, like a normal number line. By adding the negatives into that triangle, we've managed to create a negative number line, 1, 2, 3, 4, 5, 6, 7, 8, 9, yep, into infinity, yep, going in 2 directions. And then when we combined the negative and the positives together, the negative triangles and the negative squares and all that, we actually end up with a square number series. And it doesn't matter if you go for triangles or if you go for squares, the number of shapes inside is still going to be the same. Now, this is very, very interesting when you start to think about all the ways that, we qualify the universe with square numbers. Everything from like the nature of light, you've got the inverse square law and all of this stuff. And there's all of this sort of mathematics of squaring that you can find. And you can have a look at that. Equals MC. Oh, you got it. Yeah, that's right. Squared. Yeah, so obviously even Einstein was thinking into this stuff. But the fact that it can be a triangle and the fact that it can be a square is often overlooked. So let's see how that might balance out, because the triangle is actually moving, as we said, in a certain direction. Of course, we could draw the other triangles in there. But if you look at the square, it has a different direction. It's orientated differently. Yeah, that is, of course, unless we rotated the square. Yeah, then if we actually rotated the square, it would head in the same direction as the triangle. But it wouldn't, because look, this would also rotate, and you've got another line running that way. Yeah, from that side, you've got another line that can run back up that way, and another line that can run back up that way. Yeah, so there's something very different there about the triangle and the square and the way in which these orientations of each build. Yeah. So let's underline this one. Square numbers are also triangular. So let's say it again. Square numbers are also triangular, right? So it doesn't matter what square number you take, you can make a triangle version and you can make a square version. Yep. And that's very important because these 2 shapes are the only shape that can fill the second dimension, that infinite 2D plane, with just 2 colors, a positive and a negative. And from that, we can start to extrapolate that there might be something very interesting going on with this idea of squaring, yeah? That might be a little bit more interesting. Let's take Pythagorean theorem, for example, yeah? So if you have this is a classic Pythagorean triangle, you probably remember this from school, 3, 4, 5. That was a nice little number, isn't it? 3, 4, and 5, all adds up fantastically. And if you square the 3 and you square the 4, you get the square of 5. It's a Pythagorean theorem, isn't it? Yeah. And often when you see it written, you'll see these squares like that, and you can say every square in there you can place in there, and every square in there will go around the outside, and it will fill that square of 5 perfectly. It was a perfect geometric proof, as it were. Yeah. And it went down a storm in the Pythagorean days. They were really crazy about that stuff. And I wonder if anyone ever thought to tell them, or if they knew about the fact that you could also write it like this. Because if you could, they would see automatically that their prized triangle, the labna, is actually situated right here on the base. And I think that would have actually thrown them into a complete and utter frenzy at the time if they'd discovered that. Yeah, but maybe they didn't, or maybe they did. We don't know. We don't know. And so there we have everything there. We could say triangles and squares all can be utilized through Pythagorean theorem. Yeah, just had a nice little message on the Facebooky thing. So we'll go back to that in a sec. So as I said, can we have a positive triangle? Yeah, and we can have a negative triangle placed like that. Yeah. So can we have a negative square? Let's have a think. Oh, there we are, look. If we have a negative square, we can place it at that angle, can't we? Yeah, because then all the angles will run in accordance in the opposite directions. You have one going left and right there, one going left and right there, one there and one there. That will be 8 directions. Yeah. So there are differences between squares and triangles and how we can construct them out of dots, if you like. And at the same time, there's similarities because they can be divided and have the same number series. Yeah. So let's have a little think. Yeah, we've got the odd numbers here. Let's just show how that works. So we show how these numbers compile themselves. If we have the number 1, which is our first one, and we add the number 3 to it, yeah, what do we get? We get the number 4. Yeah. So you can see how these two odd numbers adding together can create the next number there. Yeah. And if we go there, 1 plus 3 plus 5, what do we get? We get the number 9. Yeah. That's the next square number. So you can see how we can build square numbers from these odd numbers that we were talking about, these odd triangular numbers. Let's see if we go over the other side here. We can say 1 minus 1 plus minus 3 if you like, yeah, and we get minus 4. So we're going back the other way now, yeah? And so this is, in a way, a kind of mathematical proof of how negative square numbers can come into existence if you decide, and it's only if you want to, if you decide that you want to define the definition of a squaring function in a slightly different way. Just slightly different, yeah? And in order to do that, we would have to go through the logic of having something called a negative square and a positive square to see that actually that can be achieved, yeah? So there's something interesting about mathematics, yeah? So I hope you like the odd bit of math, and I hope that's been a little bit interesting, yeah? And it's just also note that all prime numbers, with the exception of number 2, are odd. So actually, what this is also building from odd numbers. And so actually, whatever happens, those odd numbers will be prime numbers, yeah, eventually, yeah. And so if you're into prime numbers and all that sort of stuff, you might see that prime numbers are the root of all mathematics, they say, yeah. So therefore, we could say prime numbers are of much importance when it comes to this sort of stuff, yeah. And yet all of these odd numbers, which are primarily primes, except for number 2, will in effect form triangular and squares as well. Interesting, right? Okay, we're going to take a quick break, yeah, and we're going to catch up on some messages, yeah, and we're going to have a little look at atomic theory. Now, while we take the break, I just remind you, we do have a lovely little classroom here, and I'd invite you to come down for free to play along with us today in our classroom environment. And all you have to do is go to intoinfinity.com/live, and you can come and join us in the classroom for free and watch the presentation. But as well as that, you can enjoy or engage with some of our challenges today. Now, I said one of our challenges, could you make a triangle out of a square? Yeah, and we made this one, and we placed another one inside of, out of a circle compass. So if you want to know, you can have a little play around with some of that, yes. And basically, all you would need really would be this circle here. You can start to see I click there and I click there, and I start to make nice circles, yeah? So see if you can compile those together in such a way that you can make a triangle. And if you want some help, yeah, doing that, you can click on the little light bulb here, the little brainy thing here, and we can see that some people have actually managed to complete the challenge already, yeah? So here they are uploading their videos, yeah? So, their images. So you can go to, when you've completed your image, you can go here to GeoGebra and you can hit the export image button, and then you can see it will download it for you, yeah? So fantastic, and then you can have a go at uploading it using our little light bulb character, our little brainy character, must get those two right. And a little brainy character there will sort of allow you to suddenly upload here. You don't need an account. This is dot storming. You don't need an account. You just come here, create a guest account, and then you can just upload your image. And we can see how many people and what type of qualities of shapes we've got. Now, someone here has been rather advanced as well. You might see they've actually created a square from circles. Yeah. And if you're feeling rather adventurous, you can try and actually take some of that up with you. In fact, can you create a triangle using compass? Can you create a square? Which one was harder to create? And what does it tell us about the relationship between circles, squares, and triangles? That's the questions, yeah? So if you want to, you can also add a little comment. Now, also, what happens is we also get to vote, yeah? So we can see that one there. We can say, that's very nice, yeah? I could write a comment on that. I could do something like that if I like, yeah? And I could also make a vote. So you can also vote for him. I can click on the little arrow. I like you, and I like you, because you're the first to arrive, and so you win my vote. Yeah, I've got one more vote left. So let's see who's going to claim that one, if we can find anyone. So just to say, you can go online, you can go to GeoGebra, or you can come to our classroom to do that. Yeah. The other little thing is, because we're talking about squares and triangles today, we've got Answer Garden. We've set up a nice little play here for you, and then we're just asking you to brainstorm and find out what could you say about a triangle. Anything you can think of, just type it in that box and press enter, and anything you can think about to do with squares, absolutely anything, and we'll have a look and see at the end which answers came out top. Yeah. So I started the thing off. I said it's got 3 sides, yeah, and I've got this one here. It's got 4 sides, yeah. So you could have a think about that as an idea. Yep. So we're going to take a quick break there as I catch up with some of our messages on the Facebook and various things. And if you're up for it again. And if you're up for the game, then basically do come to infinity.com/live where you can join in the classroom fun. Okay, let's just see if we can swap back a second. There we go.